my pleasure to introduce the next speaker, Shrey Sanadhya, who will be speaking about periodicity of joint cotiles in ZD.
Okay, thank you. I want to thank the organizers for giving me this opportunity. It's my pleasure to be here to celebrate this occasion. It's a great honor to be given this opportunity. So my talk is on the complement part. It's about periodicity. You love a periodicity, you all do. But sometimes you want some periodicity too. So I will only talk about translation talents. So these are translation talents in ZD. And I have to thank Rachel for setting this up for me. And she has given a wonderful introduction of translation talents and her result. So now I can just directly go to the meat. But I will take, and this is joint work with Tom Meyerovitch and Yaar Solomon. So we have a finite set F, and I've used this double subset notation to denote finiteness. A finite set F, and we have set A of ZD. And by this notation, F directs on A, I just need to translate F with elements of A, this geometry. And that's the pointer. Okay. Which one is the pointer?
At the very top.
At the very top. Oh, I see. So we say that F tells ZD by translation, if I can find set A, says that F directs on A is Z. So I'm just moving. This A is the set of translations. And I'll call F set tile and A cotile. So I also want to introduce one more notation which was already introduced by what's happening? Okay, now I do. Okay, I have to use my mouse. So I also want to introduce this convolution notation, which was introduced by Rachel already. So in this convolution notation, the tiling equation just becomes the indicator function of F convolved with the indicator function of A is equal to 1. So we say that a subset of ZD A is periodic if we can find a finite index subgroup L such that we add L to A and we get A back. So this is what I call periodic. So when I say periodic, I mean D periodic. If I have to specify D minus 1 periodicity, I will say D minus 1 periodicity. So why periodicity? And we have seen this again and again because it helps to us with decidability. And by decidability, I mean, can we find an algorithm which can decide whether or not a finite set F of ZD can tile Z or not? And again, this theorem we have seen it many times. Periodicity implies decidability, and hence it is very important. So this tells us that we want to know the structure of the cotiles. In particular, we want to know if it contains a periodic element. Thus, the celebrated conjecture of Lagarde and Bohm suppose that F tiles Z and F tiles Z periodic, which means that if there is a subset A such that A is a cotile for F, can we find A prime such that A prime is periodic, and this is D-periodic, and it is also a cotile for F. So I want to spend some time in talking tools that go in proving such thing for B equal to. So let me show some results. These results we just saw in the talk of Rachel. Newman proved in 1977 that every tiling of Z is periodic. So we don't have to find A prime. A itself is periodic. Right? The cotile itself is periodic. We don't have to find another cotile. And Bhattacharya, he put out his preprint in 16, but I'm putting it here at 20. He showed that he proved the periodic tiling conjecture for Z2. And in particular, this tiling problem is this tile in Z2. So now I'll spend some time. I think this is a very so Bhattacharya uses algorithmic theoretic tools to prove his work, and in 21, Rachel and Tao they put out a paper and they improve his work and they use combinatorial techniques. So I'll spend some time in discussing these techniques. So I highly recommend both of these papers. These were the two papers that I really started with, and I learned a lot from them. So I will introduce one more notation, which is piecewise one periodic. And what does that mean? That just means that if I can partition my set A is for piecewise one periodic, if I can partition it into finitely many parts, and each of this part is one periodic. So the first step in the proof is to get something like this. And this proposition says that if A is a cotile for F, then A is piecewise one periodic. And then the next step would be to upgrade, which is that if I can find that A which is piecewise one periodic, then I can find A prime which is periodic, which is two periodic. So I can upgrade from one periodicity to two periodicity. And together these two gives me, because the first proposition says that every A is one periodic. So together these two gives me the periodic tiling conjecture in C2. And that was the technique that was used to do this. So let's spend some time on going through what are the ingredients for proposition 1. So to prove the piecewise one periodicity, it's proved using. So first step is to show that the indicator function of the cotile can be represented as 1 minus some function Pv, where V is in F minus 0, and each Pv is a function from 0 to 0, 1, and it is QV periodic, where Q is a constant. Okay? So we can represent our the indicator function of the cotile as sum of some one periodic function. This is a very strong result, and what goes into this to prove this result is the dilation lemma, which has been talked about a few times already by Professor Kari and Rachel. Dilation lemma just says that if F is a finite set, G is the functional cotile. So this means that 1F converted to G is 1, and that QB constant, which I have explained what it is, then there exists that every R, where R is 1 mod Q, if I dilate my tile with R, then then G is also a cotile for this dilation. So using this dilation lemma in a clever way, we prove the periodic decomposition theorem. The next step, and this was done in the paper by Greenfeld-Tao, that they use that is QV mod 1 is a polynomial. Their sum is 0 mod 1. And if you take two of them and take their supremum, they're bounded above by 1. And this all information together with the periodic decomposition theorem, Wiles equidistribution theorem, and we can use this information to deduce that there exists a finite index subgroup gamma such that the restriction of one of A on each co-set of gamma is one bigger. And that's what we need. And Wiles equidistribution theorem is an important tool that we use here. We use it to avoid the equidistribution and get periodicity. Avoid the case where it equidistributes. Okay, so that's in the core, the proof of piecewise one periodicity. Okay, any questions so far? So the second step is to prove this upgrading the period. And I recall what upgrading meant. I meant that if we have if the cotile has piecewise one periodicity, then we can find a cotile with A prime which has two periods. Okay? So what we do, how we go about that is first this observation that the set of cotiles form a Z2 subscript of finite type. And Professor Karg already talked about this. And this next theorem is the theorem 3.1 whatever that has been talked about so many times. And here is the ergodic theoretic version of it, or topological version of it, that if you have a Z shift of finite type that admits one periodic point, then it also admits two periodic points. It's just a topological dynamic version of it. And this helps us to upgrade the period to two periods. Okay. So now our natural question is, what next? Can we upgrade non-Newmans and Bhattacharya's result? Can we generalize it? And obviously, we cannot do it. This is a great result, and we just heard about it. That there is a large enough P, is that every cotile of F is non-periodic. There's an example. There's an F such that every cotile is non-periodic. So hence, we cannot naively expect to do anything. So we give a slightly different setup. And in this setup, our result coincides with the result of Bhattacharya. It holds for all D greater than equal to 2. And it also generalizes Newman's result. So let me talk about that setup. So to do that, I would have to introduce one more definition, which is that of joint cotile. So we have these tiles F1 to Fk. They are K tiles. And I say that A is a joint cotile for this tuple if A is a cotile for each of them. Okay. Let me use. Oops, what happened? Okay, so some trivially, if you think about this for a minute, then if A is a cotile for F, then A is also a cotile for F plus any vector V in the V. And you can also use the dilation lemma. If A is a cotile for F, then there exists these R's, which are given by the dilation lemma that A is also cotile for R of F. So these trivial cases do not give us any information, so we have to put some restriction on our tiles, and that's what we do in the next definition. So here I'm defining what you mean by independent tiles. So if we have K tiles that want to have K, we say that they are independent tuples of cotiles. If I pick up V1 from F1 minus 0, V2 from F2 minus 0, Vk from Fk minus 0, and this is an independent group of vectors. Okay. The usual definition of independence. With this definition, so first of all, let me give an example for this. So F1 is this blue element 0, 0, and the black points, and F2 is blue and the red points. And you can check that if you pick a point from F1 and a point from F2, F1 minus 0 and F2 minus 0, 0, then they are linearly independent. And you can also see that Z cross 4Z is a cotile for both of these tiles, F1 and F2. So here is an example of an independent tile, and A is a joint cotile for both of them. So with this definition, I first recall the theorem of Newman. Newman proved that every cotile of Z is periodic. And here's our result, that any joint cotile of D independent tiles is D. And furthermore, you can also do this for functional cotiles. So if F is a bounded function, and F is joint cotile for D independent tiles, then it is D periodic. So next, for our next result, I have to introduce one more definition, and which is more or less hyperplane independence definition. So if we have D minus 1 tiles, F1 to Fp minus 1, we say that this tuple has property star if first of all they are independent, and if I pick vector tuple U1 to B D minus 1 and U1 to U B minus 1 from F1 minus 0 plus Fd minus 0, then they almost lie in different hyperplanes. What is that? I mean by that, almost is the span of B1 to BD minus 1, if the span is equal, then Ui is equal to Vi for all i's up to D minus 2. We allow that D minus 1, U D minus 1 and U D minus 1 to be not equal. Okay? So it's a weaker condition than hyperplane independent. So with this condition, so let me first recall the theorem of Bhattacharya, which is that if F admits a cotile, then it admits a periodic cotile. Now our theorem is that if we have a tuple which has tuple of D minus 1 tiles, which has this property star, then and it has also a joint cotile A, then we can find a joint cotile A prime, which is D periodic. So the next step, we also showed that this independence property and this star property is also necessary, and in the following sense, that now we are going from the opposite direction. So if I assume that F admits a periodic cotile, which is A, then I can find these sister tiles. Then I can find these F1 to Fp minus 1 these tiles such that and a joint cotile A such that F1 to Fp minus 1 together with F is independent, and F1 to Fb minus 2 together with F has property star. So this result gives us the other direction. So together we have a complete characterization of periodicity. So this is like if F tiles C periodically, F tiles C periodically if and only if you can find sister tiles and cotiler A. Thus the A is cotiler for F1 to F2 minus 2 and F. And this whole tuple has the property star, and A is joint cotiler for F also. And for F here. Yeah. So this completely characterizes both the directions. Okay. Any questions?
So in the interest of time, maybe we could just take a single question, because I'm sure we all want to have some coffee. Is there any questions for Shrey? Neil?
How hard is it to find the sister tile if you're given the...
It's not too hard.
So it's constructed.
It is constructed. So basically, I can give the construction. I don't have a pen. Yeah, it's constructed. The other direction is harder. This